I'll talk about aerial and satellite image analysis with minimal labeling. We heard from multiple people this morning that machine learning often is a mapping of X to Y. The problem is that we don't have a lot of examples of Y. So this is a project with lots of different people. Lots of different people from Microsoft, but also from other academic institutions and governmental institutions. So some people here, their faces. As Stella mentioned, this is part of the AI for Earth program that Microsoft is running. And we started this by doing this land cover mapping project where a couple of years ago, where the idea was to map the United States at a 1 meter resolution with labels such as turf, road, building, and so on. And we started with this data we got from our collaborators at Chesapeake Bay Conservancy, where they have labeled 150,000 kilometers squared at a 1 meter resolution. But that's only 2% of the United States area, and the United States is like 2% of the globe. And as you can imagine, this is useful to have especially if you're going to do deep learning, you need a lot of data. But you can imagine that Chesapeake doesn't really look much like Nevada or Arizona or Texas. So there is a huge problem with what in machine learning they're called domain transfer. How do you use a model trained in one area in another to work in another area? And it turns out that even if you train in the south of this area and test in the north, you have a drop in performance. So this is what the data looks like. It's a very large, actually, area with several states. And it was broken into these tiles. We were doing experiments where we would train in the south and test in the north to see how well things transfer. And this is one of these tiles, 16,000 by 16,000. If you zoom in, you can see what the quality of the data is. Here, it's all labeled into 4 categories: impervious surfaces, trees, fields, and water. And then the traditional mantra in deep learning is, yeah, sure, just give me examples of these inputs and outputs. I'll train a sophisticated model like this. This is a unit that's typically used in segmentation tasks. It processes images through several blocks of convolutions that you see here, going from the top of the network down into the U and then up to the high resolution prediction. You are at every one of these stages, you are kind of reducing resolution and grouping information from distant pixels until at the very bottom of the network, you have some sort of representation of the entire scene, and then you go back all the way up. And then you have these side connections as well that give you the information from previous levels of processing. So it's somehow magically, you're going to put all of this together. And the idea here is that maybe you'll recognize that this pixel in the middle of the road is road because you see all that context around, you know the roads are long, you know that the buildings are around the roads and so on. Turns out it doesn't really work that well. It doesn't work in that way at all. It seems like the effective receptive field is only about 11 pixels in the end, you know, just so you know. But regardless of that, it works fairly well, works like magic, but it looks at very small effective receptive field area. But the problem is still that we don't have labels everywhere in the United States. So if you train this model and try to predict something in Bellevue, you might see water everywhere. So then what do you do? And so the talk actually is about various ways of coping with this problem. So the first one is using human in the loop. So all these labels have to come from humans. Somebody has to label these things. And the typical approach is this active learning approach or optimal experiment design that Omar mentioned, where maybe you train a model and then you study the model weights or uncertainty and so on and decide which type of data would be most useful for the model to be improved. And that's the active learning process. And this idea of figuring out what to label is called a query method. And it turns out in active learning, this is a very difficult thing to do. And it depends on the application a lot, how you're going to do it. And in deep learning, in particular, it's very hard because deep learning models don't know what they don't know. They have high levels of certainty in their predictions. In fact, you can even fool them by changing the images slightly and get a completely different output at the end. And so, so we designed this system that I'm going to actually really briefly demo for you, where the user who's supposed to be labeling doesn't just get asked to label a certain area, they can choose where they want to label. And how do they choose? They can say, well, let's see how well my model is working currently here. And it's not that bad, but there are some bad predictions here for in the building, so I'll label that. Yes, I'll label that. Now this is correct water. Well, these fields are correct, so I'll tell it that it's not making a mistake there. There's some trees, and then I'll retrain. Now, when I retrain, I'm actually not training the entire network, I'm training the last several layers so that this can happen very quickly. And so now I can look around and see how well I've done. Well, here it sees water in the trees now. So, well, okay. So let's tell it that these are trees. It's also seeing these shadows. So let's retrain there. And so you get the idea. After a little while, this thing starts to work. And so the difference here, as opposed to the traditional ways of doing active learning, is that the human who's in the loop is not simply a label oracle. They are actually model builder. Or you can think of this whole thing as sort of a Photoshop for the human who's doing the land cover mapping. So it's an example of hybrid intelligence. And the question is, when you do things like this, do you actually manage to do this faster with less labor, so to speak? And so we ran this study. We just, oh, okay. So we ran this study where we used 50 mechanical Turkers who worked for 15 minutes each in each of the 4 different areas in New York State, overtraining these models, always starting with the same base model was trained in Maryland. And then we had 2 adaptation methods. One was retraining only the last layer, and the other one only the last 2 layers of the fine tuning. And then each had been using one of the adaptation methods 3 times, and then another one the last time without knowing that. We didn't tell them that. And this was with randomized orders and so on. It was designed to see what are the users are actually developing a theory of mind, what are they actually becoming better at doing this fine tuning, and what are their performance drops after they move to a new model. And the short answer is yes, they are getting better, but this is the interesting result sort of from the practical point of view. And that's that if you ask them to label randomly selected examples of different classes, then users don't do as well as if you let them choose what they want to label. So they are much better query method than the various types of query methods in active learning. What I'm not showing here, but it's in the paper. You can, it was in AAAI last week, but you can find it on our website and on archive as well. When you try these sophisticated active learning methods, none of them actually work better than random for these neural networks. And then there are also these super users who are very good at this, and they, in about 15 minutes, get to 90% accuracy and 70% IOU. And also, this is the map of where people actually worked on, where they clicked. And you can see that it's far from random, sort of like an attention map of a sort. So that's one way of, and of course, it's much cheaper than Chesapeake actually took 10 months and $1.3 million to get that data. This is getting only 4 classes rather than their 7, but it gets to roughly the same accuracy with much less effort. And you can think of then of the problem of this machine learning hybrid intelligence problem, which is always a hybrid intelligence problem because the labels have to come from somewhere. You can think of it as basically lifting this labor accuracy curve. So that's one way to avoid this problem of lack of data. And we're working with World Bank on mapping Ho Chi Minh City. Now, the other way of dealing with the dearth of labels is to use labels that are maybe not at the resolution that you want them, but are just some sort of constraints that tell you what the labels might be in that area. And in particular, I'll talk about these NLCD labels, which maybe many of you are familiar with. These are issued by the Department of Agriculture NLCD stands for National Land Cover Database, and they're at 30-meter resolution, whereas we were working at 1-meter resolution. And they're 30-meter resolution because they use Landsat with many more bands to make this data. So while we do have in Chesapeake high-resolution MAPE imagery at 1 meter, and we have corresponding labels at 1 meter, everywhere in the United States, not just in Chesapeake, we have labels like this. Now, obviously, I mean, they're not that beautiful, but we have them. And what these say is that you have different types of urban environments, higher intensity or lower intensity impervious. Then you have trees and fields. Actually, have more classes. You have 20 classes. And so one way is to think about how can you actually use that sort of a combination. Like you have 1 meter imagery and 30-meter land cover labels. And with that, you want to predict 1 meter land cover labels. Now, a deep learning researcher would immediately say, okay, so I need some examples of the triplets, right? But we want to do it without triplets because in the rest of the United States, we actually don't have the high resolution data. So the idea is this: let's train a network that makes high resolution predictions, just like before, but we will change how we evaluate the predictions from that network. Because normally we would just do a cross entropy between the high resolution labels and the high resolution predictions. But when we have just these sort of labels, what we at least know that in this sort of area, we should have less impervious than in this area. And these are actually defined like this by NLCD. They say what percent impervious you have, what percent different categories you have. And you can also fine tune these statistics based on the parallel corpus we have in Chesapeake, where we have high resolution, low resolution labels. So we know, for example, developed open space will have almost no water, but we'll have forest and field in roughly the same ratio. Built will be only 12%, and then developed medium intensity will have 64%. So then we can basically say that we will count the labels that we predict in the high resolution block, and then compare it with the block of the NLCD, and that's going to be our cost. If you want a block diagram of this, the idea is that you have your semantic segmentation network, whatever it is, it makes high resolution labels Y, but then in each 30 by 30 block, you do label counting, you get some statistics, the mean and variance of the counts, and then you match it with what you expect from the labels, NLCD labels over there, and that is a KL distance, and so it's differentiable, and you can then backpropagate to the whole network and train it without ever looking at any high resolution labels. Once you're done training, then you can predict these labels from images and just throw away the top here, or you can try to balance the NLCD labels with the predictions from your input X and do something in between. Now, I'll show you how well it works in an example. So this is the pair of images that we just have this image X and the high resolution, low resolution label C, and we have lots of examples of that. I'll re-represent these labels in terms of these statistics over my 4 classes like that. And that's what we start with. But as the model learns, you'll see what happens with the iterations of learning. This is what it looks at the beginning. And then after a little while, you start to see that structure emerge and the block structure kind of go back. There are some errors at the beginning because it thinks most of these things are fields, but then eventually the model is able to work out the high resolution picture here. So again, we started with this, end up with that. It works in other areas, especially in pathology images. It's interesting to do these things where you really don't have a lot of data, but lots and lots of input images. Now, the third thing that I wanted to mention is this idea of local self-similarity analysis. So if you are going to have to use some new data or some new information, then it's often better not to take lots and lots of it, but to focus locally on an area where the variation is limited. So what do I mean by that? If you look at this image here from Lake Mead in Nevada, as I go from one year to the next, you see dramatic changes. To your eyes, they're probably not dramatic changes, but if you look at the colors are completely different. And then there are shadows also that change. But what is true in each of these images alone is that you know, this dry area over there, the pixels that are in the dry area stay similar to each other, right? When you go from one to another, they might become very yellow, but in one area, this year, they're kind of gray. So I can model that sort of self-similarity in the image with very simple generative models. How many of you are familiar with mixtures of Gaussians? Well, some, okay. So very simple model. It's a hierarchical model. And the idea is that C is this NLCD class. It's usually defined for 30-meter blocks, but I want to now define it for every one of the pixels. S is a mixture component index. So I have 32 different types of colors, let's say, in the image. And then X is the observed image feature. For now, let's just say that it's color. And then I have this generative model per pixel where my mixture component S, one of the 32 possible ways things can look, will generate the pixel X just by drawing from a Gaussian with some mean and variance. And then the link between my C, the NLCD class, and the mixture component S is just a table of probabilities. There are 20 NLCD classes. Let's say I have 32 different types of pixels in my image, different colors of pixels in the image, like quantizing the image in colors. And I have the table that's 20 by 30 that describes this. I can train this and the whole thing with EM or whatever, just fit to this thing. And the one thing that I'm going to keep fixed is the categorical discrete prior over these classes C. And what I mean by that is I'll take what I know about from NLCD, and this is NLCD from 2010. I'm actually using it in 2013 and 17 when things have changed completely. And so here I've got this blocky structure here, but of course I need to blur that structure because it's not clear whether, you know, where the boundary here between water and the scrub and brush is. But also I should blur it because the landscape shifts, especially when the water is involved. So I actually blur it quite a bit. And by that, I mean that now in that prior of mine, every pixel is distribution over the 20 classes. I'm just showing it as a mix of colors that represent those classes, using the weights appropriately. So that here, mostly I have water. Over there, mostly I have scrub, and other places some sort of a mixture. I can build all sorts of other priors. For example, I can take a prior that combines the NLCD with the open street map and some building footprints that I know, or I can do that point labels that the user put in. So I can make priors, right? Now, once I have the prior, I can train the model using EM, and here are a few iterations of EM. What I'm showing in these iterations is how the posterior distribution, the Bayesian, you know, posterior, the base posterior, Bayesian rule, base posterior is being updated as the parameters of the model are fixed, the parameters of the color palettes, as well as these translation sort of probabilities from NLCD classes to these natural segments in the image. Now, this is another thing that I can do. I can change my observation probability distribution to be a local histogram. Then I get a much nicer sort of clustering, natural clustering of things. I can do it to be a histogram of histograms. In fact, I can do all sorts of models there, and I can talk to you about those later. And then in the end, when I'm done with that, I can look at the change from 2 years, 2010 and 2013 and 2017, and I can see that Lake Mead is receding. The changes over there. It works in urban settings as well. That's the prior. This is the NLCD. That's the prior we built, as I described before. These are the two images. And here in the upper left corner, in the second image, you can see new buildings being constructed. And this actually works even without the street maps, just blurring the NLCD. I can reconstruct this high resolution map. And so the last thing I'm going to skip in the interest of time, but I can talk to you about that and that later. It has to do with using more sophisticated appearance models in that mixture model. And they're basically these very large epitome models. The reason that one thing that I mentioned before is receptive field in neural networks is fairly low. So we may as well go back to the unsupervised models and get similar results. And I'll just finish with this. If you want to get our papers, they're at ak.ms landcover. The building footprints are, you can find them here on GitHub, and then the OpenStreetMap you can find anywhere, but this is the one that we use for making the priors. So that's it for me.
We have a couple minutes for questions.
Have you looked at constructing high resolution shoreline data, specifically in tidal environments, just to be clear?
Yes, we actually we have. I can show you the browser of the whole. We were working on making one for New Orleans area for Louisiana. But yes, and also we were talking to Chesapeake about their wetlands. We were in the tool that I was showing you. You can also add new classes and build new categories. But also we are working on using these NLCD, sort of preliminary NLCD maps and super resolving them and finding differences.
My question was, if you're in a tidal environment, your shoreline changes with time.
Yes.
NLCD has a specific time frame.
Yeah, yes.
So how do you make sure that you're in a high resolution area imagery?
Yeah.
It's reference to the same tidal data.
Well, basically the way we did it was to say that there's high level of uncertainty. So as you saw with our prior, it is actually highly uncertain. The blurring is humongous so that it can allow a lot of shift. So the idea is that it can depend on your land cover type as well. Water will move a lot, especially in tidelands will move a lot. The buildings will not move that much, but you're not likely to see a building in the middle of nowhere. Like so this method would have missed the a brand new naval air base somewhere in the middle of nowhere because it doesn't expect to see it there. But if you have the hundreds of meters a year, that this can track, because the models, you can also build models to go through time. So they're just tracking things as you assuming that there is a smaller change between 2 consecutive years than 2 distant years. So all these results we're using deliberately a very old NLCD on a new terrain.
Thank you very much. So I'm very interested in the spatial uncertainty assessment of your work. So if I said right that you are completing a thematic map, like mapping the land use classifications, right? So have you done some spatial sampling to compute the errors or the uncertainty of your
the errors? Yeah, you do get that if you use the proper Bayesian model, as we discussed before. You get uncertainties. So we do get all of these are probabilistic predictions, and I was always mixing the colors to show you. So when you see clearer color, that means that I'm more certain in the analysis than when it's mixed. So yeah, we do have some estimates of uncertainty as well.
And what's the computational complexity of the work?
It depends on what you do, and it's analyzing one tile that's like 7 kilometers, 6 kilometers is like I don't know, 20 seconds. It's similar. All of these methods have kind of similar computational load. We computed the high resolution map for the United States in about 10 days on 40 GPUs. So that's about it.